contain 5 questions on 7 pages, etc. I think you're familiar with this. So for you can use calculator for the online exam. All right, let's start with the first one. So row hammer attacks. In this case, so let's read the question. So given the following DRAM bank, so this is a single DRAM bank here. It shows cells that are vulnerable to bit flipping. Okay. And the X kind of show location of vulnerable DRAM cells. So it's the leaky DRAM cells that if you repeatedly hammer could lose its charge. All right, so the first question is which row should the target data to attack be located in, right? So the data that you are targeting, where should they be located? So this one is pretty simple. So you locate them in a row that can change values, right? And the row that can change value are row 2 and row 4. They have the leaky capacitor that can change value. 2. Okay. Next one is which row should be hammered. So which row should be hammered? You can look at this one. So in order to flip the bit here, which row you should hammer? Like should you keep on flashing, etc. The neighbors, right? Yeah. This neighbor. So row 1 and row 3. Now, if you want to flip this bit, which row should you hammer? Or 5. Yeah. So
because 1 and 3 only gets you the top one.
yeah, 1 and 3 only flip bits in row 2. So the reason why you try to hammer both neighbors is because you're racing against time. You want to be able to flip it before the DRAM refreshes itself. If the DRAM refreshes itself, then the charges in a capacitor are restored. Right, so then it's basically here, row 1, 3, and 5. Yeah, you can, in fact, I mean, a more refined way is that if it's row 2, I will hammer 1 and 3. If it's row 4, I hammer 3 and 5. But, you know, there's only one space, so you put all of them. Any question? Simple, right? So next one. Suppose there's a system run process A that is controlled by the attacker and process B and C, and they are also process B and C in addition to the operating system. The memory has 8 physical page frames. So you can see there's like here, 0, 1, 2, 3, 4, 5, 6, 7, right? Has 8 page frames of which ownership is shown in the diagram below. So for example, page frame A belongs to process A. Page frame 1 belongs to process B. The page table maps A address space to the physical memory indicated by the arrow. So the arrows are basically the content of the page table. It contains the mapping between A's virtual address or pages of A to page frame of the physical memory. Suppose that utilizing a row hammer attack, the attacker can alter one of A's page table entry. Okay. So the first question is list all the pages of which their PTEs could be targeted for alteration. So a page table entry contains the pointer that maps page in virtual address to page frame. Okay, and because of that, then the pages for which their PTE should be targeted are the valid ones, the one with the valid mapping, right? If for example, if you target this, let's say page 1, it does not have any mapping, right? So if you flip it, you change it, it doesn't work because A will not access page 1. So basically, you have to look at what are the pages that have valid PTEs. Yes.
Why is 6 and 7 also a destination that we can alternate? Like, why is 6 and 7 not important?
6 and 7? No, 6 and 7 we cannot. They don't have valid mappings.
The errors of the map.
Yeah, the arrow goes for page 5, page 4, 3, and 0. Right?
Oh, I meant the second one. Sorry, question. The
Second question?
yeah.
Oh, we're not there yet. Hold on. Still first one. So this one is page 0, 3, 4, and 5. They have valid mappings, therefore we can expect process A will be using them. Okay, using the pages. All right, so that's the first question. And then the second question will be list all the page frame. Okay, so now we are talking about page frame. Okay. What are the page frame that can be the destination of the alter PTE if the attacker wants to read or write data of process B? Okay. Yeah, so very good. I mean, I think the answer is you know very well, so it's pretty clear. So one is because this page frame is the only one that B has. But let me just say a little bit more. Basically, the only gateway to accessing or to check whether you can access certain page frame or not is your PTE, your page table. Okay. So if your page table says you can access the page frame, then you will access the page frame. Now, in a normal PTE, this page will map to its own page frame. Like for example, this one. Okay. It will access. You can read and write to page frame 0 that belongs to A. But if the row hammer kind of change this one such that now it points to something else, then the page table allows you to read and write to that page frame. Yeah. So that's the reason, right? Okay. Next, so if you want to corrupt or read from from process B, you engineer a page table entry, flip some bits so that the pointer changes to point to page frame 1. Then the last question is list all the page frames that can be a destination of an alter PTE if the attacker wants to read or write data of the operating system. Okay, so in this case, what are they? Well, page frame 3, right? And page frame 5. So this is 3 and 5. Right. So if we change one of the pointer, the PTE, to point to those, then we can access kernel page. Now, I think in a revised problem, sometimes I put the page table somewhere, right? So let's say instead of A, this is a page. No, cannot be that one. Let's say instead of this is a page table. If the question is like that, then you can also include page frame 6. Because page table is just a kernel data structure. Is that clear?
Say that again.
Page table is just kernel.
Okay.
It's a special type of kernel data structure. All right. Question? No? Let's move on. Constant time expression. Okay, so this problem number 2. Now, let's look at part A. The following pseudocode perform key search on an array. The content of the I think there's a bit of a error. This should be array The content of the array and the fact that the array is sorted are known to the attacker. The attacker wants to infer a secret value of the key by figuring out how long the code runs, like how many iterations it runs. So the original code looks like this. The key is secret, and then it has a function called boolean, returns boolean, key found. The input is a key. So it starts with assigning result to false, and then it basically visit every element of the array, and then it compares the key, right? Now, once the key is found, let's say there is a match, then it doesn't continue the loop. It just go into return, right? So it breaks from the loop and go out. Now, the problem here is basically the number of iterations is dependent on the value of key, right? And this is what the attacker can extract, can observe by just timing, by timing the execution. Now, if the key is not found, of course, it will go out of the loop at the end after you visit all the element, and it will return result, but result has been assigned initially false. So it will return false. Is this clear, this part? All right, if it's clear, then let's look at the second, the first question. So first question, transform the code so that the number of loop iterations is independent of the secret. Although you may still have secret-dependent conditional branch. Okay. So our job here is to make sure the number of iterations of the loop is no longer dependent on the secret. So the problem with the above code is this part right here. We return early from the loop. We break the loop early. So we have to remove that, right? And what we can do is basically just whenever we find a match, then we just record that there is a match, but we don't get break the loop, right? So in this case, it's sufficient to just say the result, assign a new value. That's it, right? With this, then basically we hold. Let me make sure my microphone's on. Okay. Whew. Okay. So result is true. We just record. We found, but we don't break the loop. That's it. Any question? So there is still a problem though, because here, okay, it's not the same problem. So we used to have a loop, secret dependent loop termination, right? But now that's no longer there, but we have something else. We have a secret dependent conditional branch, right? So the second part asking you to remove that. Okay, so following from part A, transform the code so that there is no longer secret dependent conditional branch. And you are given already some expression, right? So so far everything is the same except for this. So there is a compare result. So compare result is basically we are subtracting the array element value with a key. Okay. If they are 0, that means they are equal. And then we invert it so that the compare results becomes true. So what can we do knowing that there is a match, right? So what you can do here is basically take the old value of result, or it with the new value with the comparison outcome, right? So if the old value of result is false, and then the compare result is true, then we will record true. right? So if the old result is true, then it's true, then it stays true. Okay, that's it. So with this, then we get rid of the if statement, right? There's no more condition. So the source of side channel disappear. No question? Move on. Part C. All right. Part C is you are given a following pseudocode. It depend on secret A and B, right? So if A or B. And then depending on the path, you assign either 100 or 200 to X. Now here, there is an assumption that there is a CMOV instruction. So there is hardware support now. CMOV instructions available in the following format. So value is true, value is false, and then Boolean. Okay. Transform the code to constant time expression, relying on a conditional move instruction. Okay. The first one is basically prepare the condition, right? So, oops, hold on. So this we want to capture as a single Boolean value, right? Because the CMOV only accept one Boolean value. So here you calculate, actually, or it's like or like this. A or B is captured as one Boolean, B or A or B. Okay. Now once you have that, then the rest is easy. So what value should be assigned to X? It will be either 100 or 200, depending on the value of B A or B. So you can see also here, like with the CMOV, with the hardware support, the constant time expression is a lot simpler. Doesn't have a long arithmetic or logic expression. But of course, CMOV depends on what processor. Some processors don't have CMOV. All right, no question? Move on. All right. Maybe of all the questions, this may be the fun part. I remember when I was teaching logic design, I brought home like 150 exam papers on Carnot map, etc. And my daughter at the time was like maybe 5 years old or 6 years old, something like that. She was fascinated with what I'm doing. Like you look like you're doing a bunch of rectangles with 0 and 1. That sounds fun. It looks like tic-tac-toe. So enjoy this, okay? This may be your last time playing tic-tac-toe, in the final exam. All right, so question 3, constant time expression minimization. In the following code, there is a branch dependent on secret ABC, and it looks like this. So secret ABC, if A, you assign 1 to X, and then if not A, right, then you go to the second one. If B and C, and you assign 2 to X, else you assign 3 to X. And the steps are already given in the exam, so you just need to fill in the blank. Okay, so here, what you need to do is fill in the truth table. Okay, fill in the truth table. You have to kind of follow the logic of this. You have to enumerate a possibility. Right? So if A is true, right? If A is true, then the other values don't matter, right? B or C. X will be assigned a value of 1. So in this case, you look at what are the cases in which A is true. So it will be these 4 cases, right? A is true. So for those cases, X will be 1. All right. So we're done with this part. Okay. So now let's look at the else part. So in this part, it all depends on B and C. If B and C, so if B and C is true only if B is true and C is true, right? So then you look at those cases. This one, B is true, C is true. Then here X will be assigned a value of 2. Everything else will be 3. Okay. Is this part clear? Okay, I'm gonna clean up a bit. Yeah. Okay, so that's the easy part, kind of like figuring out all possible combination of BABC, and what is all the possible combination of value of X. Yeah.
Why is there two TFFs?
This one?
No, but two columns below that.
Below
Yeah, why are those two columns the same?
Just, if the.
Oh, okay. Looks like this is just typo, so should be true. Yeah. Good catch. All right, just done. So now in a quiz, typically I ask you to write down all the mean terms, but in part B, it says specify mean term that corresponds to only to the case when BA is false, BB is true, BC is false. So only one mean term, guys. It saves you time. All right, so what is the rule for mean term? So basically, oh, by the way, this case correspond to which line? False, true, false. Yeah, it corresponds to that one. So basically, I'm asking, what is the mean term for this line? Yeah. Okay, so what's the rule of the mean term? If it's false, you not the variable, right? And then if it's true, you don't invert the variable. If it's false, you invert it again. That's it. Now the fun part. By the way, feel free to stop me anytime, okay? So if it's not clear, don't be shy. I used to be very shy, didn't ask questions. But I know some sometimes I didn't ask question, but somebody else asked question. I say, that's exactly what I wanted to ask. Thank you. All right. So step number C, right? Step 2, fill in the following Carnot map with the correct values and then perform logic minimization by drawing rectangles representing simplified terms. So here, here you just have to draw. So what is Carnot map? Carnot map is just basically a truth table drawn in a different way, right? Just drawn a 2-dimensional. Now, one note is that in Carnot map, it's customary to use 0 and 1, but really, false is 0, true is 1. That's it, right? So if you see, basically, we put whatever in here in the Carnot map, right? So for example, this line right here. So for we separate the case for this and for this and for this, right? So let's start with x equals to 1. Okay, some cleanup. Okay, cleanup. Okay. Let's start with the first case for x equal to 1. So true, false, false, right? True for false is 1, 0, 0. So you look at BA is 1, BB and BC is 0, 0. So that one. So here we have a 1. Now in the problem book, I use like this, but actually maybe it's better to not use value. Just use that. Is so it's easier to to avoid some confusion, right? Next line is this one, right? So 1, 0, 1, right? So 1, 0, 1, this one, etc. So this is true, true, false, 1, 1, 0. So 1, 1, 0. And last one is this 1, 1, 1. So 1, 1, 1. Okay, done. So the number of check cells is the same as number of lines in the truth table. Now for the second case, x equals to 2. Oops. This will be just one cell, which is false, true, true. So 0, 1, 1. So 0, 1, 1. For the last one, x equal to 3, that will be here. False, false, false. So 0, 0, 0. 0, 0. Here. And 0, 0, 1, right? 0, 0, 1. Here. And finally is 1, sorry, 0, 1, 0. 0, 1, 0. That's it, then. So if you do it correctly, then there should be the number of check boxes. The total should be the same as number of rows. And they should correspond also. Like there are 4 of them here, 4 of them. For 1, for 2, there's 1. For 3, there's 3. And not only that, they should not overlap, right? Because each cell is represents 1 row. So if they overlap, you make some mistakes.
How are we going to write this in there? Like how would it appear for us?
Oh, it's not projecting, right? We probably don't ask you to draw the Carnot maps. I mean, you probably draw the Carnot map on your own, and then you enter the logic expression. But I can look. You always have good question. I wish I had that good sense of to ask questions like that when I was student. Uh, well, it would doesn't allow me. You're not seeing this, right? Yeah. So Yeah. Yeah, we don't you would have to draw the Carnot map on your own. Okay, we don't draw it for you.
So we put zeros, check marks, 1, 2, 3.
Yeah, just like this. Just if you draw it yourself, you have to be careful one thing, which is so the progression is 0, 0, 0, 1, and then 1, 1. Right? It's not 1, 0. You see? 0, 0, 0, 1, 1, 1. So the decimal value of this is 0, 1, 3, 2. So that's a little bit out of order. And for a good purpose, I mentioned in a class that the adjacent column changes just by 1 digit. That's why it's like reorder like. Yeah, if you don't reorder, you will get wrong answer for sure. All right, next, okay, next the fun part. Draw a rectangle. Each rectangle will be one term, okay? So what is the rule of the rectangles? Draw as big as you can, right? But it has to be power of 2 in size. So for example, is this power of 2 in size?
No.
Yes. Is like 1 by 1, right? The size. 1 by 1 is 2 to the 0 times 2 to the 0. But is it the biggest you can draw? No. So that's not it. Yeah.
Well, she just said like, it's gonna go about volumes like anything 1, 2, 3. So, why is that the case that we don't include 0?
1, 0?
Yeah, so it's like 0, 1, 0, 0, 0, 1, 1, 1. I didn't be included.
We have 1, 0.
Like when we're drawing, it says be careful.
The check mark is to tell you which ones to coalesce with the truth table, so that you can see that you can achieve that.
Sorry, but I think I'm not understanding your question yet. So
basically,
why we put the check mark?
no, the check box I understood that.
Yeah.
Based on the table, but like when we're drawing near about a quarter.
Yeah.
How are we supposed to draw it on the exam? I think it's the question. Like how, when the exam, like, how are we supposed to? Yeah.
In the exam?
Yeah, how are we supposed to draw it correctly? On paper?
On
Yeah.
paper, yeah. So you put you partition BA, BB, BC, however you want. In fact, you could be BC, BA, B, but as long as you do it the right method, so you get the same answer.
So we have to upload a photo.
No, you just work on your scratch paper. We don't.
And to do it is that BA is close with 0 and the 1 that's on the left.
Yeah,
That's the row, and then it correlates with BB and BC from the top row.
right. So I basically BA, I pick BA for here. Like, so if BA is 0, if BA is 1. Does it make sense?
It correlates with the, so if you see the top, 0 and the 1 are supposed to correlate with the top.
Okay.
Yeah. BB is the first digit of all this. Right? And BC is the second digit of all this. Oops. Was that your question or something else?
Yeah.
Yes. Okay.
I have this thing again on it. You're asking me how you're gonna draw like, the tables themselves when it's not provided. It's not, it's the result you get from the set. Yeah. But the assumption is.
So you're gonna have to draw this on your own on piece of paper. Okay, continuing. So what about this? Can I draw this rectangle?
No.
Why? It's not the largest. Also, there's one more problem, right?
Sound bar.
Not power of 2. This is 1 by 3. 3 is not power of 2. So that's not. So what should be rectangle look like? Should be like this, right? Yeah. After I draw one rectangle, I check if I have covered all the cells. If I have covered all the cells, then that's it. Move on to the next. And here, there's no other choice. There's only one rectangle like that. Now, the last one is a bit trickier, right? What kind of rectangle can we draw? So we have to cover the cells, but there are 3 cells. That means the rectangle may overlap, right? So this is the first rectangle. Okay.
You do the,
And then you do the one that kind of wrap around.
that makes more sense. You were showing it to me earlier.
Yeah.
Cool. Well,
So is this clear? Yeah, okay. All right, so each rectangle corresponds to one term. So let's derive that. Okay, this rectangle, what is the term corresponding to it? Actually, all you need to do here is to kind of look at the value of BA, BB, and BC. Okay, it's pretty simple. So these all these cells happen when BA is 1, right? So then the term include BA. And then this rectangle span across when BB is 0, but sometimes 1, right? So 0 and 1, which tells you something, which means the value of BB doesn't matter, doesn't determine the rectangle. If the value of BB includes 0 and 1, it doesn't determine the rectangle. That means it should not be included in the expression of the term. So no BB. And what about BC? Then you look at the second digit. Well, it's both 0 and 1, right? Then they are not included. So that means done. That's it. That's our first term. Very simple, just BA. And then the second one. All right, so this happens when BA is 0, right? So that means it's not BA. And it happens when BB is 1, right? And it also happens when BC is 1. So this term is basically not BA and BB and BC. And if you look at the mean term, because this is a one cell, just one cell, this looks like the mean term for it. And in fact, it is the mean term for this. So this is just the mean term for a cell of size 1. It's basically just the mean term. All right. No question? Let's move on to the last one. The last one is trickiest. So let's start with this. Okay. That rectangle spans 2 cells, right? What's the value of BA for this rectangle? So this rectangle only spans cells that in which BA is 0, right? Yeah. So that is not will be part of the expression.
and it's
And then we look at BB. BB is 0 and 0. Oh, so it's constant, right? So that means not BB is part of it. Oops. Yeah. Finally, we look at BC. BC is the last digit, so it's 0 and then sometimes 1. So that means it's not a consistent value. That means it doesn't determine this rectangle. So that's it. So BC is not in the expression. Final rectangle is this one. Okay. This rectangle, what is it? So we do the same exercises. So for BA, is this rectangle always when BA is 0? Yes, right? Let's move up. Okay. And then we look at the BB. BB is 0 here and BB is 1 here. Oh, inconsistent. So BB does not decide this rectangle. So we look at the last digit, which is BC. 0 and 0. Oh, BC is always 0. That means it's part of the expression. There you go. That's it. Any questions so far? Now, something that can help you to kind of like figure out if you made mistake or not. You can see the bigger rectangle, the bigger the rectangle, the fewer the variables in the term, right? So this rectangle has 4 cells and therefore it only has 1 literal. But this one has only 1 cell, so therefore it has all 3, etc. So, all right, so the final expression is basically the multiplication of the value and the terms. Okay. Now, if you don't do logic minimization, this will be multiplication of the value and the min terms. But because we already simplify them, we say terms. Okay. So for case of 1, it be for this one, right? It's multiplied by what? By the term. The term is BA. Done. Right? Next, for add, like +2 times the term for x equals to 2. So not BA and not BB. Okay, sorry. BB and BC. The last one for 3. Now we have 2 terms, so we have to list both terms. It's not BA and not BB, or, so you add or, not BA and not BC. That's it. If you want to double check your work, you can always plug in numbers and plug them in, and you can kind of verify. Any questions?
No.
Okay. Move on to number 4. Side channel. Suppose that in a prime and probe attack, the attacker has finished priming the L1 cache and let the victim runs. Then the attacker reaccesses its data and times the access latency for each set. Right? The L1 cache has 8 sets. The data is plotted below. So from this data, it can be concluded that what set was accessed by the victim. So if a set is accessed by the victim, it will displace data of the attacker. So when the attacker reads it again, it will have a cache miss. Execution, the access time will be higher. So in this case, this is the execution time or access time, right? Like here for set 0, set 1, set 2, set 3, set 4, set 5, 7, 8. These all fall into a band. And it's like set 6 that is kind of like way above, right? Outside the band. So set 6, we can conclude, was accessed by the victim. All right. Consider the following RSA code, which you have seen many times. Now, suppose the attacker can trigger a page containing the code above to be shared with the victim. Okay. Of the following, which attacks are enabled? So now you can share a page containing the code. So what can be used? First of all, if you remember all the flush plus anything basically require shared page. And because the code is shared, you can identify which part of the code lies in different cache blocks. So this become enable. Okay. Now, the question is a bit, I think you have to be careful in reading the question. So what about prime and probe? So prime and probe was possible before. So it doesn't become enable just because the page is shared. So it's already, you can already do it without page sharing. So therefore prime and probe does not become enable. All right, next question. For the code shown in part B, suppose that the PC address of each instruction is hexadecimal 1000 plus the line number times 4 bytes. If the attacker wants to perform flush and reload attack, the addresses that the attacker can supply to the flush instructions is what? So here, the base is okay. And then first line number 1 times 4 bytes. Okay, this is a little bit simplification, obviously, because these are high-level language code, and it's not clear if one line corresponds to one instruction in the assembly, right? So most likely not, in fact. And also there is a function, right? So function call will translate to a couple of lines, not just one line. So it's a simplification, but that's I think I rather give you this rather than give you assembly assembly code. You may have a hard time looking at that. So anyways, okay, so let's just figure out. Anyway, the principle is still correct. The program counter value of this is like that, 1004, right? And then for the next one is 2 times 4, that's 8. Next one, 12 is what? 12 is ABC. See. And then 12 plus 4, 16. So it becomes 0 again. Okay. And then here 0x 4. Yeah. Okay, there you go. So these are all the program counters address of each of these instructions. So which one should we flush to enable the flush and reload? Is this one right? So you flush them so that they are not in a cache. And if the victim executes the if path, they will bring them back into the cache. And that's the clue for the attacker to find that, okay, it was accessed. Then they can tell the value of E sub I. So then what we need to flush is instruction address right? Corresponding to the multiply. And for the modulo, yeah, that's it.
So is the answer for the practice binomial nuts on the campus is wrong?
Hmm?
It has 14 and 16.
No, it's just different base address. This is different. So both are correct. Okay. Any more questions? Yeah, go ahead.
How did you go from 1,004 to 1,008, 1,000 to 1,003?
Yes, from here. Line number times 4 bytes. So line number 1 times 4 bytes. So add 4 to this.
So you're going from the top, line 1, all the way down to 8.
Yeah.
And you're ignoring 7 because that has the data whatsoever.
It's not that, yeah. I mean, I'm not going to use it. So
Well, it's not going to have the.
it has no significance to our attack. And then this is line 2. 2 times 4 is 8. So then this becomes 8.
How does it work for line 3? Would it be 1, 0, 1, 2? If you
Line 3?
multiply them.
Yeah, so 8 plus 4 in hexadecimal is what? C.
Oh, it's a C, okay.
Yeah. Etc. So A is 10, B is 11, C is 12, etc. Until you get to 15, which is E, F, and then go back to Z. Yeah, you feel free to use calculator. Use hexadecimal calculator. It may make it easier.
And it's supposed to because it's sensitive state, right?
Hmm?
It's supposed to because it's in negative state, right?
Sorry.
It's in the if state, which is why we can supply to Bosch instructions.
Right. Yeah. In a real attack, of course, you have to see the actual assembly instruction, figure out the instruction address. But the concept is similar. All right, last one, speculative sidechain. So this one is about branch biasing. So this is the code, and you've seen this code many times. Suppose the PC address of the branch shown above. So what branch? If the branch that kind of corresponds to the if, right? Let's say the branch shown above is BCDE. Okay. Furthermore, suppose that the branch predictor used by the processor uses a 4-entry table indexed by the last 2 bit of the PC address. Last 2 bit of PC, and there are 4 entries. Okay. The attacker runs a code that has the following branches: branch A, B, C, and D. The goal of the attacker is to bias the branch direction predictor in order to induce execution of the code in the if path. Let's clean up a bit. So what we want to do is to make the branch predictor bias in such a way that train the attacker running some code that trains the branch predictor, and then later on when the victim runs execute this code, it will encounter this, and then it will predict the branch to be taken, and it will then execute this speculatively, even though it will be squashed later, but it's still executing speculatively. Is this the problem description clear? Right. So then the question is, the branches that the attacker should train to taken, which one? Well, it must be the one that maps to the same entry in the prediction table. So the PC of this one, right? All we need to do is to figure out the last digit, E. Okay. That's hexadecimal. So change it to binary. What is the binary of this? So the binary of this is 1110. Okay.
Use the online hexadecimal calculator to help us.
No, there's a lockdown browser. I think use calculator.
That's what I meant.
Yeah.
Yeah.
Okay. Don't use a browser. So the last two digits is 10. So basically, whenever this code is executed, it will consult the branch predictor, especially this entry right here. Why? Because it's consulted for any branch with the last two bits of the program counter 10. So our job is then to figure out for the attacker what branch to keep training as taken. Okay. So it's the same process. So let's say A. The last digit is 0. If we convert to binary, it will be 0000. The last two digit is that one. That means branch A maps to this. Branch B 0x0 EA1. In binary, it will be 0001. Branch B maps to here, right? So of course, you look at the hexadecimal, looks like complex, but actually you only need one digit. PC branch C is 0xB782. See, all these things don't matter, only the last digit here because it gives you enough bits. Sorry, 10. So branch C maps to here. And branch D maps to in binary it is 0011. So branch D maps to here. Okay, now you can see which branch maps to the same predictor as the victim's code. Branch C, right? So that's the one that has to be trained to taken. Is this clear?
Yeah, and you're only taking from the address, the first digit. Right? The input.
Yeah, the last digit. Okay, last one for part B. Repeat the problem in part A, but we know the processor used G-share branch predictor. Okay, so it's a more sophisticated branch predictor. It uses the last 2 bit of PC, but then it XOR it with 2-bit history register. Right? Okay, so G-share predictor. So it is known to the attacker when the branch BCD is encountered. The branch history register typically has a value of 10. So this is typically 10. And then this is 10. Okay. So we already did this earlier. So 10 for that branch. So 10 XOR 10 is what? 00, right? So that means is the victim will consult that entry for its branch prediction. So then we have to do the same thing, map ABCD which branches are used. Sorry, which branch predictor table entry is used. So yeah, so we have the following, like for A, it would be 0. You just consult the previous thing here. For A is 0, 0. This is for A. But the history register is what? 0, 0, right? So then it remains the same. Nothing changed. So then A maps to here, B maps to here, C maps to here, D maps to here, because anything XOR with 0, 0 is itself. So the branch that the attacker should train to taken is branch A. Any more question? Maybe one last exercise with Carnot map. Where's here? I'm just gonna draw some hypothetical Carnot map, and then let's see if you can find out what term it corresponds to. Okay, just hypothetical one. Four variables. And then the pattern is like this. Okay. I draw however I want. Be like this. Maybe like this. Okay. And find the rectangles. Find the rectangles, and then what term corresponds to it. So you can systematically go on one cell at a time, right? So let's say first start with that little cell. The biggest rectangle we can draw is this, right? That's one rectangle. And then we go to the next. What other possible rectangle? Nothing else. Move on, right? So this one we already have one, but we can also draw this, right? Can also draw this. How about this one right here? You can draw this. I think that's it. So you have 4 rectangles, in fact. Maybe I should use different color. It's hard to see, right? But I will. Yeah. Use green. And use black for this one. And yellow. You can see, right? 4 rectangles. Yeah. What are the terms corresponding to it? Okay. The black one is, so BC, BD that don't matter, don't decide, so it's only BA and BB. It can be not BA. and not BB. That's the black one. The red one, okay, let's do the red one. Red one span over two cells. BA doesn't decide, right? Because it's 0 and 1. So BB decides. So the red one, BB, and then let's look across this one, this and this. BC don't decide, so it's only BD. Like that. Green. For green, BA is always 0, so it's BA, actually not BA. And then not BD. Last one is yellow. This one is BA is always 0, so not BA. And BC always 0. There you go. I told you it's fun. You can take picture if you want. Yeah. You.
Would green not be, not BA and not BD? Because the value for B changes between rows 1 and 2.
Yeah, mistake. Okay. It's like what is it here, right? Right, BD. Okay, now I have to double check the other ones too, just making sure. It looks like this one is correct. The yellow one, yeah, correct, I think. Just that one's next problem. All right. See, we finished this in like the class time.